A zinc and oblique zinc 2 plus ion concentration cell is constructed in which both electrodes are pure zinc. So zinc 2 plus ion concentration for one cell half is 1 molar and for the other is 10 to the power minus 2 molar. Is a voltage generated between the two cell halves? If so, what is the magnitude and which electrode will be oxidized? If no voltage is produced, explain this result. So the voltage will be produced because zinc is a metal, okay, which can act as an anode, and it can easily oxidize. So we have this formula. In this case m1 n plus is the molar concentration for the metal 1, and then the other molar concentration will be for metal 2. So normally we take this higher concentration 1m as m2. Okay, so therefore its standard half cell electrode potential will come over here as well. In this case, the values of V2 and V1 are 0 because these are the standard half cell electrode potentials. But since in this case only one metal is there, so V2 naught is equal to V1 naught. Okay, so these two terms will cancel out in this formula. So corresponding to V2 is the cathode side. Okay, so V2 corresponding to V2, M2 will be the molar concentration. Okay, molar concentration for N plus. What is N? N is the valency. Valency in this case is 2. So M2 2 plus will be the concentration is represented in these square brackets will be 1.0 M, and similarly M1 2 plus will be 0.1 M. No, it's 0.10 to the power minus 2 M. Okay, it's 10 to the power minus 2 M, which is actually 0.001 M, or 10 to the power minus 2 M. So now we can input these values into this equation. So V2 minus V1 is 0, okay, minus 0.0592 divided by 2. This is the log to the base 10, okay, so which is equal to 10 to the power minus 2 over 1. So if you simplify it, so then this minus 2 will go outside of this log, so it will be minus 0.0592 divided by 2 times minus 2, and then that will be the log 10. So log base 10 of 10 is equal to 1. This 2 cancels with this 2, and minus times minus is plus, so it will be 0.0592 volt. So a very small voltage value potential will be there, so this much voltage will be produced. Okay, the next problem, an electrochemical cell is composed of pure copper and pure lead electrodes immersed in solutions of their respective divalent ions. So for a 0.6 molar concentration of copper 2 plus ion, the lead electrode is oxidized yielding a cell potential of 0.507 volt. Calculate the concentration of lead ions if the temperature is 25 degrees centigrade. So for 25 degrees centigrade, you can apply this equation, and we know the values of these parameters in this equation. So the potential is 0.507. Okay, 0.507 volt is equal to, so V2 and V1 are the standard half cell electrode potentials. So in this case, what will be V2? So we have okay, so a general guideline for using this equation is that V2 is the potential for the cathode. Okay, so cathode in this case is copper. Okay, the electron, which the one which gets the electron, so it will be plus 0.34 minus, and the V1 is the potential for the anode, so it will be minus 0.126. Okay, and then minus 0.0592 divided by 2 into log of this is the molar concentration of the anode. Okay, so molar concentration of the anode. So what is the molar concentration of the anode, which is the concentration of the lead? So for 0.6 molar concentration of copper. Okay, so copper's the concentration of copper, because copper is the cathode over here, so 0.6 it will come here. And let's say that the molar concentration of this lead, we need to calculate the concentration of lead ion. So let's say that this is X. So now we can solve this equation for X. So after rearranging the terms, we will get log X over 0.6 equal to minus 1.385, and then this will further simplify to x over 0.6 will be equal to 10 to the power minus 1.385, or then x will be equal to 0.6 times 0.0412, and then the final answer will be 0.0247, or 2.5 into 10 to the power minus 2 m. Okay, an electrochemical cell is constructed such that on one side a pure nickel electrode is in contact with the solution containing nickel ion at a concentration of 3 into 10 to the power minus 3 m, and the other cell half consists of a pure iron electrode that is immersed in a solution of iron ions having a concentration of 0.1 m. At what temperature will the potential between the two electrodes be 0.14 volt? So we need to find the temperature. In this case, we are going to use a slightly modified form, rather more generalized form for the previous standard potential difference equation. Okay, so now delta V is equal to 0.14 volt, 0.14 volt. V2 is the potential standard half cell potential for cathode. Okay, so in this case, what will be the cathode? nickel, copper, cadmium, iron. So nickel will act as a cathode in this case, okay, and iron will act as a anode. So it will be minus 0.25, and minus iron is minus 0.44. Okay, and then minus R is the gas constant. The value of the gas constant is 8.31 joules per mole multiplied by the temperature. So temperature we have to find, divided by N. N is the valency. In this case, the valencies we are dealing with are 2, because nickel 2 plus sign and iron 2 plus sign. So valency is 2. And this value F is the Faraday's constant. The value of this is 96,500 coulombs per mole multiplied by the natural log of M1 or M2. M1 is the molar concentration of anode. Anode is iron. So molar concentration of iron is 0.1 m. 0.1 m. And the M2 is the molar concentration of the cathode, which is nickel, which is 3 into 10 to the power minus 3. 3 into 10 to the power minus 3. So now we need to solve this equation for T. So on simplification, this equation will become T equal to 1161.25 divided by log 33.333. So this will be 331 Kelvin, which is equal to 331 minus 273, which is equal to 58 degrees centigrade.